Okay, so we reconvene, and it's my great pleasure to welcome Professor Antoine Heidmann. Antoine Heidmann is a CNRS research director at the Laboratoire Kastler, Brossel, and is leading the optomechanics and quantum measurement teams. I must say that I didn't know that we can put macroscopic system in the quantum state, and this is typically the topic that Antoine Heidmann addresses. We have already discussed a bit this topic at the 7th lecture when we discussed optomechanics, and so this is the notion that you can take really a macroscopic system that can have a very large mass and control the motion of this system to its quantum state, the ground quantum state. And so Antoine investigates radiation pressure interaction between light and these mechanical oscillators, and explore the quantum behavior of this macroscopic quantum system. And this leads to a very high range of activities in the group he leads, from high sensitivity optical measurements to manipulation and cooling of the motion of systems close to the quantum regime. And these developments address both fundamental questions in quantum measurements and practical applications such as reduction of noise in gravitational wave detections and development of hybrid quantum sensors. And so I'm very happy that we will have the chance to hear about this application of quantum light and the control of quantum system for new discoveries. Thank you, Antoine. Let's welcome him.
So, thank you very much, Pascal, for the introduction and for inviting me to this nice conference. So in my talk, I will try to convince you that quantum technologies can be used for something else than direct applications. Here it is for fundamental research. And namely, we are interested in gravitational wave detection. You certainly know that in this domain there were very important progress during the last decades. And I would like to show that quantum technologies, in particular the use of squeeze light, has been an essential tool to get these results. So, as Pascal said, I am working at the Laboratoire Brossel, LKB, and in the group we have different activities, but one of these activities is to participate to the Virgo collaboration, which works on gravitational wave detection, and we are focused on quantum optics and quantum optomechanics. Okay, so to start, I will make a brief introduction to gravitational waves. It is based on, it's a consequence of Einstein general relativity. And Einstein general relativity can be understood by this simple video where actually the massive objects such as the sun, the Earth, just deform the space-time structure. So with this kind of model, you understand that the fact that all the Newton laws can be understood as geometrical effects, such as the fact that the moon turns around the Earth. In this model, if you have massive objects which are moving, which are accelerated. For example, here we have a binary system made of two stars. One is a pulsar with this radio flash, because it was the first indirect observation of gravitational waves. But in this kind of system, you see that the space deformation moves in times, and then you have a propagation of the deformation at long distances. This is in particular the case at the end of the life of such a binary system, when the two stars merge. And in that case, you have violent event in the universe, as you can see. And you have a propagation of a wave, significant wave, at the speed of light, which can go far away from the source. In the simulation, at the end, you have a black hole, as you can see at the center. So, these ripples of space-time induce change in distances between free-fall objects. It's somewhat similar to what you have at the surface of water with ripples, which propagate. The difference is that the wave is quadrupolar. So if you consider, for example, here a binary system, and you look at a long distance from the system with a tube here, you will have this kind of deformation of the tube where you have alternative compression and expansion of the circle of the tube, as you can see here. So the main point is that you have a variation delta L over L of this tube, and it is directly related to what we call the amplitude of the gravitational wave. This amplitude at long distance is given by Einstein equation of general relativity, and it takes a quite simple form, as you can see here. So h, which is the relative variation of distance at long distance, there is these factors. G is the gravitational constant, c is the speed of light, m is the mass of the binary system, and r is the distance between the system and where you are detecting the wave. And you have the ratio between the speed of the masses relative to the speed of light. So it's this factor is close to 1 when the speed is relativistic. Okay, so let's give some order of magnitude. Let's first start to create a gravitational wave on Earth by artificial means. For example, if you take a cylinder like that, let's say 10 meter long, 3 meter diameter, and you rotate this cylinder at something like 5 hertz, so 5 revolutions per second. So it's not so easy. The cylinder will have a 500 ton. Okay, but if you do this, and if you are looking very close at 1 meter, you find that the amplitude of the gravitational wave produced by this kind of system is 10 to the minus 34. This means that if you have a detector of 1 meter, you have to detect the motion of a displacement of a change of size of this detector of 10 to the minus 24 meter. We cannot do it. We don't know how to do it currently. So the kind of events we want to see are, of course, violent events produced in the universe. I already show some stars collapsing here. What we want to observe are mainly black holes. The simulation here shows 2 black holes who are rotating. It's a binary system, and at the end of life, they are merging. So typical parameters, it will be, you will see in the following, the ones of the first detection. You have 2 black holes with a mass of 30 solar mass. Okay, so it's small black holes as compared to what we can find in the universe, but large compared to our sun. They are very close. They are very compact objects, and they are very close since they are rotating with a distance between them of the order of 100 kilometers. This means that you have one black hole here in Paris and the other one like Lille, I think, or something like that. Okay, and 330 mass, solar mass for each. And then they rotate at 100 Hertz at the end of their life before they merge. So they are almost relativistic. Their speed is very close to the speed of light. So in that case, Of course, they are not close from here. They are far in the universe, and the typical distance is 400 megaparsec. So 1 parsec is 3 years of light. So it means that this event was produced 1 billion years. The light took, and the gravitational wave took 1 billion years to come to us. Okay? But even in that case, which is a big event, violent event, you find that the amplitude of the gravitational wave is 10 to the minus 21. So it's small. If you, for example, take the Earth, the whole Earth as the detector, so a typical length of 10 kilometers, let's say, 10,000 kilometers, sorry. The deformation of the Earth, due to the fact that the gravitational wave passed through the Earth, will be in the range of 10 to the minus 14 meters. It is almost the size of a nucleus, an atom nucleus. It's 10,000 smaller than the size of an atom. So this is the kind of things we want to detect. So to do so, we are using very large interferometers, optical interferometers, such as Virgo, which is shown here. And the principle is just to use a Michelson interferometer. So you have, you have a plate here which divides the beam in two parts. You have 2 arms, and then you recombine the two arms, and you find here at the output some interferences, as you can see here. When the path followed by the light is changed by a wavelength of the light, you will completely change the pattern of the interference, okay? So the typical sensitivity of this kind of interferometer is just given by this expression. When the displacement delta L of the mirrors, the length of the arms, is the order of lambda, you find a variation delta E out equal to the intensity, okay? So the relative intensity fluctuation variation is equal to the relative delta L over lambda. It can be expressed just as a function of the amplitude h of the gravitational wave, just by multiplying and dividing by L. So what you see here is that the interferometer is able to see a gravitational wave with an amplification factor, which is the length of the arms with respect to the optical wavelength. So this is a good factor, and so this explains why we are building large-scale interferometers with arms of kilometer length, 3 kilometers for Virgo, which is a French-Italian collaboration close to Pisa, and 4 kilometers for the 2 LIGO interferometers in US. We have also inserted cavities in the arms. You see you have mirrors here in order to have to enhance the effect of light inside the arms. We can say that due to the mirrors round trip time, the light is performing inside the arms. We have a factor which is the thinness of the cavity, so that the effective length of the system is L times the thinness of the cavity, which is the order of 100 typically. We use as much as power we can for the incident light. So it's in the range of 10 to 200 watts. And of course, the objective is to control or to reduce all the noise you can find in this kind of system. So it is interferometry pushed to its limits. For example, it is the largest ultra-high vacuum system in Europe, because everything is in vacuum. The tube you see here are the arms, 3 kilometer arms, because you have to avoid any diffusion of light onto particles. So you can see here it is tubes which are below the Earth. It is unique high quality mirrors. It is big mirrors, 35 centimeter diameter, 40 kilograms, pure silicate, surface roughness control at a nanometer, and of course coatings, very good coatings. with loss 1 ppm. It means that you send 1 million photons, you have only 1 photon lost. The LMA, it's a laboratory at Villeurbanne, close to Lyon, Laboratoire des matériaux avancés, is a specialist of this kind of mirror, and they made the mirror both for Virgo and LIGO. You have also to control the seismic noise coming from the ground, and we use a very efficient vibration isolation made of multiple pendulum. As you can see here, you have 7 stages of wires, then intermediate mass, and so on. And with this 7 stage of vibration isolation, we obtain an attenuation of 10 to the 14 with respect to the vibration of the soul, so of the ground. Okay, so this curve shows what we obtain in terms of sensitivity for Virgo 1. So you see that the main source of noise, so this is in terms of frequency, so the frequency we want to look is in the audio band from, let's say, 10 Hz to 10 kHz. The target sensitivity is 10 to the minus 22 in terms of amplitude h of the gravitational wave. And you see that most of the noise are due to the mirror displacement. It is the residual seismic noise. It is all the thermal noise linked to the pendulum of the suspension, the violin modes of the wires used in the suspension, and finally the internal thermal noise of the mirrors because they vibrate like drums. But you see we have also the quantum noise of light here at high frequency. And this is the real life. So it shows the sensitivity of Virgo and the continuous improvements made during 7 years between the first observed run of Virgo up to the last curve, which is very close to the design sensitivity. Okay, so a brief history of the gravitational wave detectors. The first idea was in the 80s. It took more than 25 years to go to the first runs from 2006 to 2011, both of LIGO and Virgo, and at that time there were no detection at all. So both collaborations decided to build advanced detectors with a sensitivity improvement by 10, as you can see on this figure, Virgo curve here and advanced Virgo here. And the first detection was obtained in 2015. It was followed by what we call run 03 for almost 2 years, from 2019 to 2020, with the first real studies of population of events. You can see here the quantum noises in purple. So in advanced Virgo and advanced LIGO, we are very close to the quantum noise. And in practice, since 2019, there were implementation of quantum noise reduction using squeeze light. I will come back on this, of course, later on. Then the last run was in 2023, run 04. And now the 3 interferometers are stopped, are upgraded, and the next run is expected in 2027, with, in particular, broadband quantum noise reduction. I will come back on this. A few words about the first event. Okay. Okay. This is the first event observed in 2015. At that time, there was only the 2 LIGO interferometers working, but you can see here the 2 signals observed, which correspond to what I showed you before, the merge of 2 black holes. You see the time is very short. It is 100 milliseconds. It was a very fast event. It's really the end of the merger. And you see a slight delay between the 2, and this is because they are at a distance of 3,000 kilometers, the 2 interferometers. So the wave took 7 milliseconds to go from the first one interferometer to the second one. Okay, so before for the 01, 2, 3, there were at least 90 events detected and recognized as events. And you see here all the events that have been observed. When it is black, it means that it is black holes, binary system of black holes. And most of them are black holes mergers, which were not at all expected. We expect neutron star events, binary system of neutron stars, and actually it was much more black holes. There were 2 events corresponding to neutron star, here and here. And it was very interesting because in that case, the 3 interferometers were working all together. So it was possible to detect, to define the source, the direction of the source with very accurately. And then there were more than 50 telescopes, either in optics, infrared, gamma ray, and so on, who look at this point in the sky, and they found a signal, all of them, in their domain. And so there were a complete reconstruction of the story of the black hole, of the neutron star merger, and then what happened after for a few weeks. And it was very interesting because they found results very impressive concerning the production of heavy molecules and so on. And it is really the beginning of a new era of multi-messenger astronomy, including gravitational wave as a trigger. 10 years later, the first observation, it was around 04. And you can see here the great improvement in signal quality between the one in 2015 and the one in 2025 for the same kind of event. So for the last run 04, it was the longest campaign, 2 years and a half, 250 events detected. Much of them were black holes merger. Several rare astrophysical phenomena, such as very massive mergers of black holes of more than 200 solar masses, which was not expected at all. Second generation merger, it is something interesting. We observed merging of black holes, which are themselves the result of previous mergers. And some tests of fundamental theory of course general relativity, in particular in a highly nonlinear regime. Okay, so to obtain this kind of results, I would like to demonstrate that, to show you that quantum mechanics is essential to get the sensitivity needed to make this kind of observation. So, of course, you know that light is subject to quantum fluctuations. Photons emitted by light, photon you have in light has a random distribution in time. So if you look at the intensity of a light beam as a function of time, you find a Poissonian distribution with some fluctuation like that, meaning that if you look at the frequency, the noise spectrum as a function of the frequency, you have a flat spectrum like that with a level which depends on the intensity, of course. So in the case of gravitational wave interferometers, I already write this equation giving the signal as a function of the amplitude of the gravitational wave. We have cavities in the arm, so if you look at the minimum amplitude you can detect when when you compare the signal to the shot noise, you have something like that. It's just the reverse of this equation with here the shot noise spectrum. And you have also the cavity finesse, which appears as a low-pass filter because you decrease the capacity of the gravitational wave to detect high-frequency gravitational wave when you go outside the boundaries of the cavity. So it looks like that in practice. And this is the curve I already shown for the sensitivity of Virgo 1. So for Virgo 1, it was not of great interest to improve the quantum noise because it is at high frequency, and at low frequency, most of the noise is due to classical noise, thermal noise of the pendulum or of the mirror. But this was not the case in advanced Virgo, where the sensitivity is 10 times better. So for advanced Virgo, for example, it has been implemented in 2019. The fact to inject a squeeze light source in the interferometer. So what you see here is the squeeze light source and all the optics that is used to send it in the interferometer. It is a very specific light source because you have to work at low frequency, 10 Hz to, let's say, 10 or 100 kilohertz. So it's in a low frequency band. And you need, of course, a lot of squeezing. So you can see here the characteristic of the squeezer with a very flat response from, let's say, 10 Hz to 100 kilohertz, 10 dB below the shot noise. So it is injected in the interferometer. And this is the result, where you see as a function of frequencies the sensitivity of the interferometer. So in black, it is without injecting anything in the interferometer. And in red, it is with the squeezing light injected in the interferometer. So I forgot to say that it is injected in the output. Okay, it enters the interferometer by the output. So we obtain a 3 dB reduction of noise, because mainly limited by the optical losses we have in the interferometer, because it's not specifically designed, was not specifically designed for quantum purposes. But it's still important because 3 dB means a volume that can be accessible to detect gravitational wave at 3 dB. It's a factor term in terms of volume. What you can see here also is the fact that if you look here, for example, the red curve is above the black one. This means that when we squeeze, we send squeeze light, we have extra noise at low frequency. And this is not a surprise, but it's the fact that we have not only the shot noise as a limit, but also quantum radiation pressure noise. And so I would like to discuss this in more detail. When you consider the interferometer, you have two conjugate quantum noise actually. So the one I already discussed, which is a laser noise, you send fluctuation of a laser with fluctuation inside the interferometer, and at the output you have this fluctuation which are reflected. But you have also the fact that you have radiation pressure effects of light inside the arms, which will push the mirrors. And since you have fluctuations of the light inside the arms, you will have spurious mirror displacements, which will also create here some noise, which can limit the sensitivity. And this kind of two conjugate effect of laser noise and radiation pressure effects was first studied in the 80s with this seminal paper by Carlton McCabe in 1980, which has really motivated the emergence of quantum optics in the 80s and quantum automechanics in the 90s. So just a word about quantum automechanics. So the idea is to study in more details how radiation pressure can couple the light, the quantum fluctuation of light, and the motion of a resonator. So the idea is to put a mirror onto the resonator and then put everything inside the cavity, so that to have a strong coupling between the field of the light field and the mirror. There is mainly two interests for that. The first one is to understand the quantum limits in displacement measurements. Of course, for gravitational wave interferometers, but more generally speaking, for this, how the measurement can, and the radiation pressure can perturb the measurement. It's also a way to develop sensor working at the quantum limit, and very compact sensor in general. And the second objective is to use this coupling to to control the state of the massive and macroscopic object, the resonator. Because we can perform laser cooling, similar to atomic laser cooling, on this resonator using the light, and then study the frontier, as we say, as a frontier between classical and quantum worlds, using massive objects and the interaction with gravitation. I won't enter in details into this, but it is a very active topic. I would like to say that in France we had the chance to have a fruitful exchange between our community and the gravitational one, thanks to 3 people actually, which developed, which had since the 80s many discussions and meetings. I would like to say a word about them, because Philippe Touranque was a theoretical physicist. Alain Briet was a French father of Virgo. There was a French father and an Italian father. And Serge Renaud is a researcher, now emeritus researcher at the lab, at the LKB. So they developed a fruitful discussion, and it was a starter for all quantum optics and quantum optomechanics, at least in our lab and I think in France. Okay, so I come back to what happens when we consider radiation pressure noise. For the sake of simplicity, I only consider one cavity, not 2, so only one arm, let's say. And what is important in this case is to look at the phase reflected by the phase of the light reflected by the cavity, because the phase will create the interference observed at the output of the interferometer. So you have something like that. The phase is proportional to the length, to the change of length delta L, times the factor which is the cavity thickness divided by the optical wavelength. And now we consider that the light is quantum, so you have a Wigner distribution, so a Gaussian distribution of quantum noise around the mean field in phase space. And so this produces a phase shift between the input and the output of the cavity. And you can detect this phase shift only if it is larger, of course, than the noises. And you have 2 noises. You have 2 quadratures for this distribution, one parallel to the mean field, which is the amplitude noise, quantum amplitude noise, which is so related to the intensity noise. And you have the quadrature perpendicular to the mean field, which is linked to the phase noise, delta phi in. Okay, so when I put quantum noise in this equation, you have 2 added terms. The input phase noise, which simply come back and appears in the reflected field. And you have the fact that the intensity noise will produce a displacement of the mirror due to radiation pressure, which is actually proportional to the intensity noise here, delta I, times something which is a mechanical response of the mirror. Okay, so in the case of gravitational wave detector, it is mainly the suspended motion to the wire of the mirror which is important. So it's a low-pass filter in this range of frequency. So it looks like that. The displacement decreases with frequency for the radiation pressure effect. And for the phase noise, of course, it is flat, as I already said. I neglect here the cavity bandwidth, which is at higher frequency. Okay, so now if I increase the intensity of light sent in the cavity, radiation pressure effect will be larger, of course, because you send more light. So you observe here that it will increase like that. And the phase noise will decrease because they are conjugate variables. And so the phase noise goes down like that. So at the end, you have the same kind of curve, but it is displaced on, so that if you change intensity, getting smaller or higher intensity, what you do is to translate this curve, and you can never go beyond this line, which is the standard quantum limit. So this has been demonstrated, for example, using optomechanics. So it's a thin membrane inserted in a cavity. It has been done in 2018 by Albert Schlisser. And this is what he obtained. So in that case, it's not a low-pass filter, the mechanical response, but it is a resonance. And if you look in this region here, with this zoom, you see that when he increased the intensity of light, the shot noise is reduced, while the radiation pressure is increased, so that he can never go beyond the standard quantum limit. So it is, of course, the same for gravitational wave interferometers. And this is why the curve I showed you for Virgo, advanced Virgo, you have a decrease of shot noise at high frequency and a slight increase of radiation pressure noise at low frequency. But it is possible to go beyond this standard quantum limit using squeeze state. And the way to do this, so I reproduce here the equation I already shown, is to send, if you send a phased squeeze state, so that you send a light beam in the cavity where the phase noise is reduced, while the intensity is increased, you will observe something like that. The phase noise is reduced, while radiation pressure is increased. So you have this kind of red curve instead of the green one. If you inject intensity squeeze state, that is to say an ellipse squeezing perpendicular, so that the phase noise is increased and the intensity noise is decreased, you will have this reverse effect where you increase phase noise and you decrease radiation pressure. So in practice, it is exactly the same as if you change the intensity, okay? Except that it is simpler to, when you are already at the maximum intensity you can send in the interferometer, you can add squeezing to improve the sensitivity, for example, at high frequency, and this is what is done for advanced Virgo, for example, and LIGO too. But the point is that you can also choose another angle for the ellipse, different from perpendicular or parallel. And in that case, you see that you have this kind of intermediate sensitivity curves, intermediate between the blue one and the red one, okay? And in that case, you see that you go beyond the SQL. And this is because you have correlations in this expression. You have correlation between, when the angle is not parallel or perpendicular, you have correlation between the phase and the radiation pressure noises. And you can do better by just adjusting at every frequency the angle of the ellipse so that it corresponds to the optimum. And in that case, if you can rotate the ellipse with frequency, you will have a sensitivity curve like that, where at every frequency you improve the sensitivity with squeeze state as compared to when you don't send squeeze state. So you can obtain sensitivity improvement over the whole bandwidth. This is easy to do, to rotate the ellipse, just by sending a squeeze state, a standard squeeze state, in a cavity, which is slightly detuned, so that you have to choose, both the detuning of the cavity with respect to the resonance of the field, and the bandwidth of the cavity, so that when you cross this, the cavity response, as you can see here, the ellipse is rotated from one position to the other. So this is what we are doing in Virgo. We have the corner frequency of the frequency is about 50 Hertz, which is very small. So we use a very long cavity, 300 meters, something like 285 meters. So the squeezer here sends its light in this cavity, and then it is injected in the interferometer. So you can see here the installation of this long 300 meter long cavity close to the north arm of the interferometer. So it works. The work is in progress because it's not yet connected to the interferometer. But it has been done also in advanced LIGO. And you can see here the result. So the black curve is when the sensitivity is out nothing. And what you see in purple is the sensitivity when you send the proper rotated squeezed field. So you observe that we have improvement of the sensitivity over the whole bandwidth. You see, for example, with respect to here, the green curve is obtained with a phase squeeze state, so that in that case you increase the sensitivity at high frequency but not at low frequency, where it is decreased as compared to when you send nothing. And you can do better by rotating the ellipse. So this is a quite recent result, 2023, and the idea is to do this kind of techniques for the next run of 5. Just a word about what we are doing at the lab. First, we want to make the same kind of techniques on systems, tabletop experiments with small systems, in particular nanomembranes. And in that case, we want to test various advanced techniques, of course, sub-SQL techniques like the one I presented you, but also other techniques. And we also participate to the collaboration with another group, the Calva group at Orsay, on an intermediate scale system made of a long cavity, 50 meters, and with a high finesse cavity, 30,000 finesse. So you see here the installation at Orsay. So the idea is also to test what happens in a gravitational wave interferometer with a system which is simpler because it is a little bit smaller. But it has suspension and so on, like the same kind of suspension as Virgo. Okay, so I'm coming to the conclusion. So first of all, I hope convince you that quantum control is essential in gravitational wave detectors now. They are working at the quantum limit, and squeeze light, at least standard squeeze light without the ellipse, rotating ellipse, is now routinely used. It has been essential to make the last observation. The next step will be to perform broadband quantum noise reduction. The fact to go to an increased sensitivity will improve, of course, the detection range. So we will have even more events. We will have a better low frequency sensitivity where radiation pressure effects are dominant. And this is important because we will detect the end of life of the binary system at a time previously less. Well, we can detect the story of the binary system over a larger time. And we expect to access to new source or rare events. At a longer time, longer perspectives, there are alternative approaches we are testing, such as what we call variational output. I won't enter into the details, but it is possible actually to completely remove radiation pressure just by looking at something else than intensity at the output of the interferometer. By optimizing the signal we detect as the output, it is in principle possible to remove completely the radiation pressure effect. So last word, I think that gravitational wave detectors are the largest quantum sensor ever built. And second last word, I would like to thank all the team in my lab, the optomechanics and quantum measurement team, and thank you for your attention.